It's the morning. We're back for computer science. I've got computer science lecture soon, this morning after this. And it was kind of recommended to read over some of the chapter. It wasn't a due, but I didn't get through that much. I got through 20% of one chapter. That's it. So I thought I would take another session today to learn more and prepare myself for class. I've realized probably not gonna have time to go through the nitty-gritty details of my recalls every day. If I would spend, today, right now, recalling everything that I learned yesterday, it would probably take 15 minutes or more, which is fine. That's great, but I'd rather be safe than sorry currently and get through the material rather than getting every detail like perfect. Just because, as you can see with Make It Stick and linear algebra, this takes like linear algebra is like day 60 and I'm still in 1.3. So that's what happens when you recall every detail. It's great, but we're gonna try something new right now, and we're just gonna try and get the overview in like literally 30 seconds to a minute. So we learned about the overview of computers and programming yesterday. We learned about how computers are really just a bunch of switches. Switch a bunch of switches together create circuits, and circuits can create processors and memory. And processors process instructions. Sets of instructions are called programs, applications, or apps. We talked about memory, how that stores information, data in binary, just as a processor works in binary, has a little bit of memory, but it works in memory. We learned about the structure of instructions, basically location, operation, new location to store the information. Also jump starts at location 0. We learned about machine instruction and executable programs, aka executables. Those are in binary. And then we learned about assembly level instructions, assemblers, high level languages, and compilers. That is, I think that's basically everything. All right, it looks good. So I'm gonna go ahead and jump back into the textbook and continue learning more, and I'll be back to recall at the end. Just read a lot. We're in the second section now. It's about a tour of the computer, talking about the general parts of a computer. First, they kind of walk through the history of the computer name. It was originally for a person who did computations, like a worker. You needed to hire a computer. Then it evolved to be used for the large, big room full computing devices, and then for personal computers, and then for laptops, and then for smartphones and tablets, and even other electrical devices that other computing devices within electrical devices, such as things in planes and cars and Fitbit and everything else along those lines, medical devices. So computing devices really, in the modern sense, is what a computer is. Software evolved, that term evolved once, or became a term once the hardware became more, or the computers became more stable and the programs became bigger, so software became a term. And then we started talking about essentially 5 main parts of a computer. I didn't get through all 5, I got through 4. The first is the input-output devices, also known as peripherals. These are where users essentially input data and where users can receive data back, such as the monitor, keyboard, mouse, touchscreen, LED lights, microphone, camera, etc. These are peripheral devices, or aka input-output devices. The second part of the computer is the storage. And modern storage is SSD, solid state device. Solid state device is a non-volatile memory storage. Essentially, non-volatile means that when you power it off, it still stores the memory. It is a flash memory, so to access the memory, a flash of electricity shoots through the circuit to pull out the information or data or instructions, I should say. Information is a different term, really. Yeah, we haven't talked about data information yet. But yeah, flash memory, non-volatile. It replaced hard disk drives, hard disk devices, hard disk drives, I think, which were magnetic disks that spun but were slower and more expensive than SSD. Then we talked about memory. So there's a difference between storage and memory. Storage is typically talking about SSDs or hard drives, and memory is typically referring to RAM, random access memory, which is volatile, meaning it's short term, it goes away after it's powered off, but it's really about holding instructions or data for the short term. Well, then what's the point? Well, it's random access, so it can access any part of data or memory or storage, I should say, any part of storage very quickly. That's why it's random access. It doesn't have to sequence through. It can go and pick which part it wants to go to. So that's that. They typically come on a circuit board with a processor. The RAM does. Then we talked about the fourth, which were processors. These are also known as CPUs, computer or central processing unit, and also known as microprocessors, which are basically CPUs that can fit in a single chip, which most modern computers are going to be microprocessors, like in personal computers. Processor executes programs or runs through programs. It's typically got its own bit of RAM for increased speed, because it can hold a little bit of the most important instructions and data in mind, rather than having to run an execution, run like a sequence of instructions to access RAM and communicate with RAM. That takes more clock ticks, is what they called it. I don't know. The fifth thing is clock. So I'm assuming that's kind of like if you're running a program, it's like line by line. Each line is probably a tick. Each instruction is probably a tick, but we're going to learn about that later today. Programs are processors. There was something else I'm forgetting now. Was there? We didn't talk about GPUs, but we talked about CPUs. The first program a processor typically runs is called BIOS. It is Basic Input Output System, which basically sets up the basic peripherals of the computer. The second program a CPU typically runs is the OS, or operating system, which allows the CPU to run other programs and interfaces. Okay. Cool. Oh, right. The information that the CPU holds is known as cache. Or not CPU holds, the RAM of the CPU holds is cache. It's the most commonly used instructions or data. Okay. Cool. Yep. Yeah. Yep. Typically a circuit board processor, megabytes. Right. I learned kind of review of the mega, giga, and tera. Mega, million, giga, billion, and tera. Terabyte is a trillion bytes, and a byte is 8 bits. So that's it for now. I'll talk to you later. Alright, I'm sitting outside of Chipotle because I forgot to recall after class, because I went to talk to my professor office hours after class. So let's try to recall what it was today. We had more lecture than usual today, because it's still early. We didn't have time really to get through the textbook. Typically it will just be mostly questions, and not so much of lecture. He said about 10 minutes per lecture per class, and the rest will be pretty much pure instruction. So what did we lecture about today? It was about 30-40 minutes today. basically the basics of the computer. Can I say that? Basics of the computer? Kind of hardware-software relationship. So you got the hardware, and around the hardware is the operating system, and this is what translates the applications or programs. The operating system translates the applications or programs or apps into the machine. Is that right? Into the machine instruction? Is the assembler within the operating system? No. I think the operating system, I'm not exactly sure there. The operating system is like machine specific, typically, right? They have different versions. Device specific, but you can have different operating system versions for the same device. But the hardware itself, the hardware itself is device specific. Oh wait, no, that's never mind. I'm getting confused with the programming languages that we talked about. All right, let's go to programming languages for a second. We got the machine instruction. That's the lowest level. That is this device specific. Then you got that's first generation languages. Second generation languages, those are assembly level languages. They are, you got some words, but it's still like very not how humans think. It's more like input, process or operation storage, input process output, IPO. All right, we got a car alarm going off. Let me think now. Second generation language, assembly languages. To get an assembly language into machine instruction, which everything has to eventually become in machine instruction, you've got an assembler. And then you've got above that, third generation languages are high level languages. Are assembly languages low level then, I think. Anyway, high level languages, these are most languages such as Python, such as Ruby, I think JavaScript, C++, and C. These need a compiler or an interpreter to translate the high level language down into the machine instruction. Python specifically uses an interpreter, but you can also use a compiler. And so essentially there's a fourth generation language that's recently come out that is known as natural language. Essentially you use an AI to program in the third generation language, which then gets converted down with the compiler or interpreter into the first generation language, which is the machine language or machine instructions, and that is binary. As far as the basics of the computer hardware software relationship, it was kind of just, you didn't go into it that much. It was just hardware, operating systems around the hardware, and then you got applications or apps or programs. So then we talked about the programming languages, and then we talked about the basic instructions, the fundamental instructions you give a computer, which are input, process, output, IPO. That's the only thing I really took away from my first computer science class that I only took for like a day before dropping, and that was a year and a half ago, just about 2 years ago now. No, 2 years. Yeah, 2 years ago in California. Then within the questions themselves in the class, on the multiple choice questions on the screen, I learned a few things. An algorithm is essentially a specific set of instructions for solving a problem. Computational thinking is thinking or problem solving, sequential problem solving, thinking in steps, problem solving in steps. Algorithm, computational thinking. What else did we cover that was kind of new? Or I wanted to solidify. Computational thinking, algorithm, something in a program. Something about value, output of value, expression. An expression in Python is something is any piece of code that outputs a value. Okay, I know we're missing one other thing, but let's just check how I did. All right, basic concepts, right, got that. That's the hardware operating system app. Programming languages, interpreters, compilers, assemblers, high and low level languages, open source languages. Open source language is kind of a language that is free to use, and also you can contribute to its development potentially. So those instructions that we learned about yesterday that were like, load this piece of information, do this operation, output the result here. That's really like how low-level languages, assembly languages work. All right, pretty solid. I will say that's pretty fucking solid. After it's been about an hour and a half, over an hour and a half since the class ended, and I was able to get everything essentially. Basics of computer programs, IPO. All right, that's it for today, or for now. I'll be back to learn more on my own, reading through the textbook later on today. So, see you in a bit. Well, I grabbed another pen. It's right there. I'm actually really excited to get back to computer science learning. We left off on studying the main parts of the computer. Like I said, I'm going to try to do quick recalls here, like literally less than a minute. We've got the input-output devices, aka the peripherals. We've got the storage, SSD, or hard drive disk, or we've got the memory. Then we've got the processor, and then we've got the clock, which we're about to get back into. And the reason I'm doing quick recalls is because I know how long it can take to recall all of the information that I learned and took notes on, but I just don't really have time. I don't know. I don't know if I do. I'm going to be rather safe than sorry, and just try to do the main points very quickly and get back into learning. I think that is the greatest balance. Not getting too caught up in the details while also maintaining main points while also retrieving. And there's 32 chapters in this book, and this is a 4-semester class. I've gone through 3 sections of a textbook in 60 days before, aka linear algebra. So yeah, I'm gonna jump back in. We're in the computer tour 2.2, and I'll be back to recall what I learned. All right, so we finished up the computer tour. Then we started the next section, which was language history, I believe. I'm gonna flip this around so I don't see anything. So the clock. A clock is basically how fast a processor executes instructions, I think. So like 1 tick equals 1 instruction executed. And so cheap processors process about 1 million instructions per second, whereas or 1 million ticks per second, yeah. And then expensive ones are billions per second. Then we started reading about the transistor and the integrated circuit. So I don't know when it was, sometime 60s, 70s, 80s, 70s, 60s. Sometime they created transistors, which are just essentially smaller switches. And combinations of these are called an integrated circuit rather than a switch with a circuit. It's a transistor with an integrated circuit. Moore's law was essentially that every 2 years, the number of transistors on an integrated circuit, or aka the size, would double, aka the size of a transistor would halve. This was true for a very long time, but recently, in the past 10 years, I think it's slowed down and hasn't held true. It's crazy how small they are now. Yeah, that's the microprocessor. We already talked about microprocessors, just small, really small processors. Um, in 1971, that's not that long ago. I think IBM in 1971 created the first integrated circuit, known as the 4004, and that had 2,600 transistors on it. Now we have computers with, I think, billions per transistor, each with a different core, which is a different, essentially, processing unit. A processor can only execute its sequential execution. So when you run multiple, if you ran multiple applications with only one processor with one core, it's a kind of an illusion uh, that it's processing multiple things at once. It's really just going back and forth really quickly, analogous to the human attention, how multitasking is, I believe, a myth, and you're really just moving back and forth your attention really quick. However, if you have multiple cores, you can parallel process because you have multiple basically processing units. Then we had a little animation, basically information, including potentially the operating systems in the SSD, solid state disk, or the storage. The memory, the RAM, pulls out the information or data from a program from solid state store, or the storage solid state disk. And from there, the processor takes the information from memory, aka RAM, into the essentially the processor and the cache. So the larger the cache, the pretty much, and the larger the RAM, the more power the computer has. The faster the clock, the more power the computer has. So there's so many levers for pulling, basically pulling to improve the power, speed, efficiency of the computer. They talked a little bit about how, due to Moore's law, RAM becomes cheaper after a few years of buying a PC. So a great way to improve a PC's speed is just to buy the new RAM and stick it in after a couple years. Programming languages. So now we're talking about scripting languages. Scripting languages are languages that can be executed without a compiler. Instead, they use an interpreter. We've got some things to learn about this. The disadvantage of script. Script is a program that can be translated by an interpreter. Whose instructions? Okay, yeah. So Python's a scripting language. Basically, scripting languages and scripts are slower. That's a disadvantage because for each instruction of the scripting language, you have to run multiple instructions, like interpreted instructions, but can be run on multiple processors simultaneously if each processor has an interpreter. So I don't exactly know the benefits. Maybe that is the big benefit. I'm too much of a noob to really know why that would be that important. Can you only run a non-scripted language? Like, can you only have one compiler or something? There was something else. I'm gonna pull it back up because I would like to understand why this is so important. Clock, processor, it's in the processor, yeah, it's an aspect of the processor. Okay. Oh, that was it. Yeah, and there were like links to videos and articles at the bottom of 2.2, but I just went ahead and didn't do them. I can always come back to them because the reason I didn't do them is because, we've got a lot more still to do on Sunday, and it's Wednesday. And yeah, interpreted execution is slower, but advantages include avoiding the compilation step. And okay, so they can be run. One of the advantages is they can run on multiple processors simultaneously if each processor has an interpreter plus, skips the compilation step. All right, that's it. Talk to you guys tomorrow. See you.